where we're going to decode the ultimate mystery of how nature builds these intricate, beautiful structures in a universe that is, quite frankly, completely driven by chaos. We're diving into the hidden conversation of crystals, the fascinating thermodynamic and molecular secrets that allow simple atoms to just assemble themselves into stunning, infinite architectures. I mean, have you ever looked at a perfectly formed snowflake, or even just a grain of salt, and wondered how billions of blind, microscopic particles manage to build something so precise? There's no architect, no blueprint, and definitely no central brain calling the shots. Yet they do it constantly, sometimes assembling millions of atoms in a fraction of a second. So today, we're going to break down exactly how this happens. Okay, let's just dive right into this. Picture a pitch-black room, filled with billions of tiny dancers moving completely randomly, and ask yourself, how do they suddenly know exactly where to stand? Before a crystal forms, these molecules, our tiny dancers, are in a liquid or a solution. They're vibrating, rotating, colliding, and just freely exploring countless possibilities. There's absolutely no pattern. It's pure, unfiltered chaos. But then, almost mysteriously, they begin to organize. They turn, they align, and they lock into very specific, rigid positions. Well, in a liquid solution, molecules have maximum freedom. They're living their best, highly disordered lives with millions of possible orientations. But in a crystal, they are perfectly fixed, ordered in orientation, and arranged into repeating patterns. And this creates a massive paradox. You see, the universe really isn't supposed to work this way. Moving from high freedom to strict, fixed positions goes against one of the most fundamental rules of physics. Because, as we all know, the second law of thermodynamics tells us the universe naturally leans into an increase in disorder, a concept we know as entropy. Entropy, represented by the letter S, is basically a measure of how many microscopic configurations or arrangements are available to a system. A gas expanding to fill an entire room, a drop of dye completely dispersing in water, that is entropy increasing. Nature absolutely loves high entropy because it means more possibilities and far more freedom. So, here is the kicker. During crystallization, entropy actually decreases. In physics, that's represented by a negative delta S, meaning a negative change in entropy. At first glance, this seems literally impossible. If nature always favors increasing disorder, a highly ordered crystal should never, ever form. By locking into a repeating lattice, these molecules are sacrificing their translational, rotational, and configurational freedom. They are paying a massive entropy penalty. So why on earth does crystallization happen? To figure out how they pull this off, we have to look at the invisible molecular language of forces where millions of weak supramolecular interactions combined with strong bonds to build something like a massive stable bridge. Molecules don't use words to communicate, right? They use these forces. A molecule doesn't say, hey, I need to sit right here. Physics simply dictates the lowest energy arrangement through a hierarchy of forces. We've got primary forces, like the strong ionic bonds in a sodium chloride crystal, but for molecular crystals, we rely heavily on secondary supramolecular forces. Think of hydrogen bonding in ice or van der Waals forces. Now, individually, a van der Waals force is incredibly weak, but collectively, oh, it's powerful. One person cannot hold a bridge together, but thousands of carefully arranged connections create a structure capable of carrying enormous weight. And this brings us to the ultimate reveal. The true architect pulling the strings here isn't just entropy, it's Gibbs free energy. This equation, delta G equals delta H minus T delta S, is the mathematical core of why order forms spontaneously. You see, spontaneity isn't decided by entropy alone, it's a competition. The universe will actually allow a local decrease in entropy, that loss of molecular freedom we talked about, as long as it's compensated somewhere else. And that compensation, that comes from enthalpy, represented by delta H, which is the energy of the bonds themselves. It's like nature is playing with a giant balance scale, weighing the heavy penalty of lost freedom against the massive reward of releasing energy through new bonds. When molecules lock into their lattice positions, they form all those stabilizing interactions we just went over. Hydrogen bonds, van der Waals forces, the whole shebang. Forming these interactions releases energy, typically as heat, and this creates a favorable negative enthalpy change. Nature's basically asking one question. Does the energy released by forming this highly ordered structure provide a big enough energetic reward to compensate for the lost freedom? So if the energy released, the enthalpy, is large enough to overcome that entropy penalty, the overall free energy drops, and boom, crystallization happens spontaneously. It's a simple trade-off, really. Entropy decreases, which is unfavorable, but enthalpy also decreases, which is highly favorable. When that enthalpy reward is bigger than the entropy penalty, the overall Gibbs free energy, delta G, becomes negative. And in thermodynamics, a negative free energy means a process will happen all on its own. The system moves to a lower, much more stable overall energy state, even though it became way more internally ordered. Now, you might be wondering, what controls this balance? Temperature. Temperature is the ultimate multiplier in this equation. Cooling a liquid actually lowers the penalty of losing entropy, allowing the enthalpy advantage to completely take over. If you look at the equation, temperature, the T, multiplies the entropy term. At high temperatures, the value of losing that freedom is massive, so the entropy penalty is huge, which is why crystals melt or dissolve. But at low temperatures, that multiplier shrinks. The entropy penalty just matters a lot less. That's exactly why cooling down a saturated solution in a lab, or watching water freeze into ice on a cold winter day, triggers crystallization. The energetic reward of bonding simply dominates the whole process. Okay, so thermodynamics tells us why it's favorable, but let's talk about the how. How does this build step by step through a mechanism called nucleation, taking us from chaotic, random collisions all the way to massive crystal structures? Nucleation explains how millions of independent molecules actually manage to arrive at the exact same repeating pattern. First, molecules collide randomly. They form these transient, unstable clusters that usually just quickly fall apart. But every now and then, a cluster reaches a specific size and geometry, where its internal interactions are so favorable that it becomes thermodynamically stable. This tiny, stable seed is called a nucleus. Once that first stable nucleus actually forms, it acts exactly like a tiny molecular computer. It serves as a repeating template that physically guides the next generation of molecules right into place. Think of a crystal not just as a frozen pile of randomness, but as pure information stored in matter. Its fundamental unit cell contains the precise instructions, where the atoms sit, how they orient, and how neighbors connect. Because adding molecules to an already stable nucleus takes way less energy than starting a brand new one from scratch, growth proceeds layer by layer. The crystal essentially copies and pastes the same structural code endlessly into a perfect 3D architecture. You know, there's a really profound philosophical lesson here about the universe. Just like a flock of birds, extraordinary global organization can emerge entirely from local interactions, without a single leader in control. A single molecule attaching to the edge of a growing crystal has absolutely no idea what the final shape is going to look like. It's only responding to the immediate, local forces acting on it. Yet billions of these individual local decisions create a breathtaking masterpiece. It's the exact same principle we see in ants building colonies or cells organizing into tissues. The order just emerges collectively. Ultimately, crystallization is just this grand negotiation between freedom and order, creating an intricate molecular poem written entirely by the laws of physics. Who is really in control here? Well, it's not the molecule alone, or the weak interactions alone, or even entropy alone. The true architect is the delicate, perfect balance of energy, entropy, molecular shape, interaction geometry, and time. Molecules willingly sacrifice their randomness because they gain something far more valuable: a stable, highly organized, lower energy existence. So what should you really take away from all this? The next time you see a snowflake or a grain of salt, remember this. Nature proves that true beauty and perfect order are just the most energetically rewarding paths available to us. It isn't magic, and it definitely isn't a violation of the laws of the universe. It's simply the stunning result of molecules finding the most stable way to exist together. So the next time you marvel at a snowflake, ask yourself, what other chaotic systems in our universe are just waiting for the right drop in temperature to suddenly fall into perfect, beautiful order?